Good afternoon. Thank you for having me. Today, we had a very interesting announcement for artificial intelligence. The world's best Go player is now a machine learning algorithm that learned how to play the game by playing against itself 5 million different games. That is a stunning achievement for reinforcement learning, a type of AI technique. However, it is also highlights one of the big problems in artificial intelligence. That is that we can create these seemingly superhuman intelligences for things like game playing, but yet we still do not have a system that has the perception and mobility abilities of a 2-year-old. Rod Brooks, one of the world's premier roboticists, talks about this problem in terms of embodied cognition. Rod believes that a lot of our intelligence is actually in the world around us. Let's take, for example, doorknobs. There are some doorknobs in this conference area that I'd never seen before. Yet I know they're doorknobs because of their position in the world. They're on a door, and they're in a particular height where my hand can grasp them. But even if I've never seen a doorknob before, I can generally figure it out because there's only a certain number of affordances for it. I can push it, pull it, twist it, turn it, and eventually I'll figure out how to open up the door. We have no AI currently that can do that sort of manipulation task. Rod believes that until we actually have a machine that can inhabit a human-like body and have the sensory and motor skills that humans have, we will not be able to relate to it. It will not have this human level of intelligence. Now, his approach to this was to make an android, a computer that had the similar type of limbs and arms and sensors as a human does. This is Cog, his robot. When I first met Cog, I tried to teach it how to fence. I did a lot of sword work when I was at MIT. And so, playing with Cog, he soon started making the same sort of hand motions that I was. But his footwork was atrocious because he was bolted to a desk. There was no way he was going to actually learn how to fence well without being able to move around. And that highlighted a problem with Rod's approach. Nobody was going to treat this robot, this 500-pound thing of metal, the same way they would a human infant. They would not teach it to speak the way a human infant learns how to speak. They would not give it the same play experiences that a human infant has to learn how to interact with the world. And so these robots, while they have the same first-person view of the world that we do, they do not get the same learning experience that we have. And what we've seen in machine learning is that we need lots and lots of experience, lots and lots of data in order to actually make a system that's successful. So I approach the problem a different way. I like to do what I call symbiotic AI. I'm trying to interweave a computer with something that's already intelligent, mainly myself. I'm trying to put cameras where my eyes are, microphones where my ears are, put motion sensors on my wrists, and have the computer be able to learn what it is to interact with the human environment by watching how I interact with the human environment. In return, I'm hoping to get an intelligent assistant that learns to be more intelligent, more proactive, and more socially graceful. Let me give you an example. Most of you have used a fitness sensor, or at least seen one being used, something like a Fitbit. Now, these systems are designed for very specific things, like footfalls, so they can track walking or running. Almost none of them are trained to do things like dumbbell exercises, like a bicep curl or an Arnold press. Instead, they're designed for things that they can actually make work for everybody when they pick it off the shelf. This is a problem. How do I would really like to have a fitness sensor that could actually watch my exercise routine and count the number of repetitions I make every day. Look for things like how fatigued I am, or actually give me encouragement to go beyond my previous limits. So what if I could make a fitness sensor that actually learned what exercises I was doing? Instead of trying to make a fitness sensor for everybody, let's make a fitness sensor for me. And that's what we've done here. Here we have 32 different dumbbell exercise routines. You can see them at the bottom of the screen. That's all 32 different sequences there. And what they represent are the individual motifs, repeated sections of data that come from the IMU, the motion measurement unit that was on the system. So this is the same sort of accelerometer and gyro you see on today's smartwatches. Now, as this person went through, this is a student of mine, went through his exercise routines, the system looked for repeated sections of data, things that looked the same. And what it discovered was the 6 dumbbell exercises that the student was doing in their exercise routine. Now again, this system had no idea that this was exercise, had no idea what that data was for. All it did was look for repeated motifs of data in that stream. And it said, there are 6 different things I can label here. Here they are, and then the human can actually label them. The system also automatically outputs the recognizers for this data. So now, if it goes back and tries to label that data, if it tries to label new data, it's 97% accurate in recognizing these 6 different exercises. We now have the ability to make a fitness sensor that actually learns from the user what sort of exercises they're doing, and then is able to count the repetitions or look for the form or give suggestions on how to improve what they're doing based on previous performance. Now this is great, but very limited. We're just talking about what you can do on a smartwatch. Can we do something more sophisticated? And the answer is yes. In computer vision circles, I'm known for my work on recognizing American Sign Language. This is me in the upper right, wearing a camera in a cap that's looking down to watch my hands. The view of the camera, it can be seen in the lower right-hand corner here. From that system, we can actually gather lots of data of how sign language is done. In this case, I had 500 phrases of sign consisting of 40 different signs. Now, can I use the same algorithm that we use to recognize fitness routines to recognize sign language, or to discover sign language, rather? The answer is yes. When we apply the same algorithm we used on that accelerometer data to this computer vision data, we actually recovered 23 of those signs. And now we're actually working on algorithms that also start recovering the grammar of sign language. Now that's very exciting. It shows that, indeed, we can recognize other forms of repeated behavior and automatically label them. The thing that we really got excited about, though, when doing sign language is we started realizing that most of what we do in the world involves our hands. Sign language is a system of language, but so is interacting with each other. Shaking hands is a form of language. Waving to people is a form of language. Interacting with my coffee cup is a form of language. And so we discovered that a lot of what we want to do in AI can be done simply by watching the hands. For example, if I have a book, I can try to judge a book by its cover, but recognizing a book is very difficult because the cover may have a picture of a tree on it or a picture of a city. Am I supposed to recognize the city, or am I supposed to recognize it's a book? It's very unclear for an AI what to do in this situation. However, if I watch the hands, as soon as I see the person open the book and page through it, that motion with the hands is very distinct. You're not going to mistake interacting with a book with interacting with a tree. You only do this motion with books and magazines. And so Irfan Issa and his student Darnell Moore showed that we could actually recognize objects very well just by watching how we interact with them using our hands. Now this is very exciting. We can now have an insight into the real world, not by doing normal object recognition, but looking at how we interact with those objects to identify them. So what might we use this for? Well, here's a particular problem that a friend of mine, Jeff Bigham, is doing. He and student Brandon White have been looking at how to help people with low vision interact with the world around them. Now, let me give you an example. Suppose you are blind and you're going to shop for a new cereal. If you pick up a box of cereal, how do you know whether or not it has nuts in it? If you are allergic to nuts, making the wrong decision could put you into a hospital. So how the blind currently do this problem is they might invite a friend along or get a personal shopper to help them identify the object and what's inside of it. Now, that's expensive and time-consuming. Suppose instead that we actually have a system where I could take a picture of the object and ask the crowd over Amazon Mechanical Turk or Twitter what's in the cereal box. So let's play a video of that if we can.
Test open glass with 2 visually impaired users. First, we show question answering, where a user asks a question and receives an answer from Mechanical Turk or Twitter, and the answer is read aloud.
Share with open glass. What does this box say on it?
Okay, glass. Share with. Open glass. Tap. What is this a can of?
Press it. Go.
Okay, glass. Share with. Open glass.
Tap.
Okay.
Speak.
What is this box?
Tap.
Swipe forward and then double tap.
I'm coming.
That worked, right?
I guess we'll see you guys.
Unfortunately, you can't really hear it's
Next-
being said there because it's using glass's bone conducting transducer, and so it sends the audio through the skull to his cochlea without announcing it to the world. So it's a more private system. So this seems like a really great problem for computer vision. Asking computer vision, what temperature is my oven set to, or what type of can is this, seems like a perfect problem for computer vision, except it's not. Most systems that do computer vision today are trained on images that are perfect or near perfect. They're well framed. They have good lighting. They're often trained from systems on the web where we have people submitting good pictures, good images of things. But when you have a camera from a first-person viewpoint, most of the images are poor. They're out of frame, they're out of focus, they're in bad lighting. Here, for example, is the VizWiz system that we just showed there being used to help somebody learn how to cook a prepared meal. So first they send an image out to the crowd, and the crowd comes back saying the instructions are likely on the other side of this box. So the person then takes a series of images trying to get the box in the right place to get the instructions out. And even when they get in the right location, you still have glare on the image that might make it very hard for that remote person to give the information to. So you can imagine a computer vision system might have problems if you just take a single image and try to get the instructions off of it. However, that same first-person perspective that proves a problem can also prove it as a benefit. If I give the user feedback locally of how to get the image into the box into the image, or even better yet, if I can identify what the user is doing ahead of time so that I can proactively look at the box as they manipulate it and offer suggestions as they're interacting with it, that might solve the problem completely. And this is work by Alireza Fathi and Jim Ray at Georgia Tech doing such tasks. They are trying to identify both the objects, the actions, and the activities that people are doing from this first-person viewpoint. In this case, they're looking at preparing coffee or making a sandwich. And the observation to note here is that the background is not changing unless the user changes it. In other words, I can make a model of the background of these objects sitting on your kitchen shelf. And until you actually move it, we know it's not an active object. And we know the hands are going to be the agents of that motion. And so what we can do is we can segment the hands out from the background, then also segment out the things that are changing as far as the objects. Here, we see that the hands are actually manipulating the lid for the coffee can. We can also look for changes to the states of the objects. Here, we've actually taken the lid off the coffee jar, and so we now know that is a significant event. From this, we can actually start looking at how to identify activities. These activities consist of bags of objects and actions, both the removing of the screwing of a lid or the spreading of peanut butter. So for making coffee, we know it involves a cup, it involves a spoon, it involves a coffee jar, and it involves a particular procedure. For making a sandwich, we know it involves bread and possibly spreading stuff with a knife. These are very disparate things that we can recognize the activity by recognizing the action. Now, if I'm trying to distinguish between making a cheese sandwich and making a peanut butter sandwich, I can do that by looking at the constituent parts. Is it cheese or is it peanut butter? But I can pretty quickly figure out what the user is doing by the types of actions they're doing on the objects. So what might we do with this? Well, for me, I'm very interested in starting small and getting big. Can we actually look at very limited use cases and then make it more and more general? For example, here's something that my friend Tony Jabara did with me 20 years ago. This is an intelligent assistant for billiards. It automatically looks at the billiards table, analyzes the shots, and suggests the shot in an AR system that you might take next. Now you can imagine this system, instead of being trained up carefully by hand, it could have just automatically discovered the game of billiards by watching an expert play. Even better yet, it could watch to see how I play billiards to give me suggestions on what shot I might most probably make next. A similar thing might be done for surgery, as we just saw. Suppose I actually watch an expert surgeon going through many, many different surgeries. Here, we might be looking at removing a tumor. And as the doctor goes to release the clamp on an artery, it might start providing the doctor, the surgeon, the blood pressure of the patient. So when he releases that artery, he knows that something bad happens. Finally, what probably matters to this audience more is, can we make intelligent assistants that actually learn these sort of expert repair tasks? Can I actually automatically learn the procedures that experts use for actually repairing, maintaining, or inspecting aircraft or printers or oil rigs or power stations? Can I have a system that automatically figures out the steps and then proactively, for a novice repairman, provide suggestions as they need it? So again, the big idea here is that I'm trying to create an AI using wearable computers' first-person viewpoint. I think we have a possibility to use the big data approach that's being successful in machine learning in general, collect first-person data from on-body sensors, and then address these problems in progressively harder domains. My name is Starner, and I'll take some questions now.